basically, there could be several things about that. It could be that, it's really interesting because Kepler does see a lot of eclipsing binaries, so many of them, but they haven't found planets around those eclipsing binaries yet. However, there are also other binaries that are either being ignored by Kepler or planets just haven't been found. But I think it's a good question. So why hasn't Kepler found around some binaries you didn't know were binaries, so just blended together in a gigantic XF? So that is why I'm thinking hard about this. But I'll say one other thing about this. Because our nearest star system, Alpha Centauri, is a binary. We're really hoping there's a planet that's terrestrial-like around Alpha Centauri. And people in exoplanets, they have kind of rule of thumb that as long as the two stars are 7 times more separated than the orbit of the planet, so that means if the planet is a unit of 1 from the star, the other star has to be 7 times further. It should be okay dynamically, that star shouldn't interfere with the stability of that closer planet. Similarly, if there's one circumbinary, it also has to be 7 times more than that separation. Okay, so we'll come back I'll have to think about that binary. I'll talk about that later. So now we'll move on to the next part, characterization. And here I'm just going to tell you a bit about what we're trying to do with all these planets. So we went through the discovery phase, and now the question is, what are we going to do with all these planets? We want to know a lot of things about them, what they're made of. Here's a cartoon showing planet interior, showing Jupiter on the left. It's made mostly of hydrogen and helium with a heavy alpha core. Okay. And it's showing other planets. This is a gigantic Neptune, and this would be a super Earth. And I want to give you one example. So this part of my talk, I am going to get into a few details here. It just will last for about 5 or 10 minutes. But I wanted to try to tell you things that are going on in characterization of exoplanets. And I have 2 reasons for doing this. One is to tell you what is happening. And the other one is to sort of help you, kind of people who really are interested in the subtleties, where we're going in the future. Because there's a very important lesson in the next series of slides. I'm going to talk about a planet called GJ1214b. This was another person, Leeds, who cataloged a bunch of nearby stars. This is a transiting, we call it a mini Neptune, some people want to call it a super Earth. This planet is about 2.68 Earth radii, the mass is about 6 Earth masses, its period is only 1.5 days. It means it goes around the star every 1.5 days. Its temperature is about 550 Kelvin. And this is heralded as the first transiting super Earth. You can get a lot of information about it. But we want to know, what is the planet made of? And I almost hate to tell you that we don't know what the planet is made of. We have a mass and a radius, and that gives us an average density. But from that information, it's very difficult to extract what it's made of. And I'm going to try to explain that by an analogy. And people from the scientific field, you can read the slides and see, you can read the notes, but for the rest of you, I'm going to give you a thought experiment. And I want you to imagine that I'm going to give you a box. I give you a box. And I say there's 2 things in the box. There's rock and there's ice. And I ask you, can you tell me, given the box's mass and size, what fraction of rock and ice is in the box? Okay? So in science, we would say we have 2 unknowns. That's the fraction of each material. We also have 2 data points, mass and radius, mass and size. And the answer is you could actually solve them. So you have 2 unknowns and 2 data points. Okay? So you could figure out what that is. Now imagine I give you a box, but there's 3 things inside. There's rock, there's ice, and there's some air. But again, you only have 2 data points, mass and size. Now I say, can you tell me the fraction of each of those? You're going to have to take this one away and think about it. If I could assign you homework for tomorrow, I would assign this problem to you. Can you do that? You can't actually, because you have more unknowns than data points. You can't figure out what the fraction of those are. And as an example, let's take an example here where water ice would have an intermediate density to rock and air. So I could take away some water ice, replace it with some amount of rock and air, and I get the same density. Okay, so actually it's a problem. We have only a mass and radius. We can't tell you exactly what the planet is made of. And in this particular case of GJ, it's a bit of a problem because people wanted to know, could this be a water world? Could this be a new kind of planet that has more than 50% by mass water, just like one of Jupiter's icy moons? That was a planet, though, not a moon, that lived in the inner solar system of its star, inner area of its star. But we can't tell you exactly what it's made of. And people wanted to know, could this be the first exoplanet with liquid water? All life on Earth is liquid water. So we're just dying to find a planet that has liquid water. But what's interesting is out of the 3 different, and the colors are just representing different amounts of iron, rock, ice, and air. But if you actually model this planet with detail, you can say basically it doesn't have liquid water. There's no way this planet can have liquid water because it's just too hot. It's too hot on the inside, it's too hot on the outside, it won't have liquid water on it. So this part of my talk is sort of to say we have mass and radius of lots of planets, 100 of them actually. We make models to try to understand what's on the inside. But because we're limited by the amount of data we have, the mass and radius, we can't go very far. We can tell you all the possibilities of what it's made of. We can't tell you exactly what it's made of. Okay, and I'm emphasizing this point because in exoplanets, initially we set out to characterize every last thing about every planet. And we're now starting to see on the horizon the fundamental limitations that face us because we can't get any more data that exists. We also want to learn about planet atmospheres. And here for the people who will come to my lecture, I'll give you a bit of an intro about how we study the atmospheres, and we do it by what we call spectrum. You can think of the spectrum as basically a rainbow. You know the rainbow you see outside? If you looked at them really closely, you would actually see black lines, parts of the rainbow missing, really thin lines and lots of them. And some of those lines come from Earth's atmosphere, from molecules and atoms that are absorbing some of the sunlight. And we essentially do that with exoplanets. And I want you to know that we have measured about, meaning collectively with people in the field, about 3 dozen exoplanets that have their atmospheres measured. This is relegated to a subset of exoplanets. We call them hot Jupiters, the big Jupiters and close to the star. And we've learned a lot of interesting things about them. We've detected dozens of exoplanet atmospheres, and we've identified molecules and atoms, including water vapor, carbon dioxide, carbon monoxide, methane, sodium, potassium, hydrogen. That's probably about it. And we've seen other things like day-night temperature gradients, and there's many other things. I have this in a review article if anyone's interested, just let me know. And I have just only one more technical slide. I'm just going to throw it out there for my astronomer colleagues because I wanted to make sure they got to hear something new. And the sort of latest, I call fact, exoplanet atmospheres is this planet, again, GJ1214b, which you can actually study from the ground. And excuse me if I just do a couple minutes of technical talk. And this is what you get people fighting over. People are taking observations, they're not agreeing with each other. They want to know if this planet has hydrogen-rich atmosphere or if it has no hydrogen. And this will feed back on helping us understand what the interior is made of. So this is sort of what people are working on now. And if you want to know what's interesting in exoplanets, it'll be everyone in the world with a telescope that can study the atmosphere of this planet is looking at it. And I think in a year or two, we'll have some kind of idea of what's going on with this planet. Okay, I'm going to skip some complicated stuff and say, yeah, I'll come back to this. I was trying to explain how we try to model exoplanet atmospheres. All you need to know is that it involves many complicated fields of atmospheric chemistry and physics. And for people who like programming, if you love programming like me, it's a great field for you. If you don't like computer programming, you probably shouldn't get involved. And we want to understand biological gases. We also have geophysics that makes volcanoes. That we have to understand all the atmospheric processes in order to know which gases can accumulate in the atmosphere. And it's not like this is mostly what my research area focuses on. So I'm going to come back to that in a later lecture. But just to summarize this part, detailed atmosphere and interior studies for dozens of exoplanets. Due to data limitations, interpretation can be ambiguous for individual planets. And it wasn't just for mass and radius interiors, it's also for atmospheres. So what I see is that Kepler is this harbinger of this new era in exoplanets. I think we're going to have to move away from individual objects. We can still study them in a limited fashion towards statistics. And with 3 dozen exoplanet atmosphere measurements, we can do statistics. So for me personally, it's a huge thing that now, after 15 years, we're able to say we have enough objects to do statistics. And although there's some disappointment that you can make a complicated model on a computer, you can make some prediction, you can't really, it's different. You can never really do we call the inverse problem and say exactly what that planet really is because we're limited by data. But we can use the statistics. And we'll have a different way of doing science for the next number of years. And that's where I see this field going. I'd be happy to talk more about this now in reception or what have you. I think it's really important for people who are working on exoplanets. I know there's not many people who are working on it, but people who are try to recognize this to see where we can make progress. And this moves me to the last part of my talk. And now I want to throw something out there because I started with the founding fathers and how hundreds of years ago, these were really visionary people. And they weren't trying to be visionary about exoplanets. They did believe it was logical that they were out there. I'm not sure if they ever really thought of how we would find them. But I want to tell you what I'm thinking about and what I see happening in other places. It's just a very few people who are thinking about this. And I gave you the whole story about exoplanets and how people worked hard in obscurity and they believed in something that might never happen. No, they believed it would happen, but the rest of them believed it would never happen. And this is where I want to get to next. And it has to do with the stars in the galaxy and how we do have nearby stars. And the stars actually are really far away. And nonetheless, they're very far away. But the question is, how can we find planets around the very, very nearest stars so that we can leave a legacy for the people who do come hundreds or thousands of years after us? Because, this is the crazy part of the talk. We are born explorers. And people want to try to send a probe to another star. Other scientists are legitimately talking about how very few scientists and engineers could we ever travel at even 1/10 the speed of light. If we could travel at 1/10 the speed of light. How long would it take to get things out to Centauri? It would take 40 years, or 0 years. Actually, I'm planning to still be alive in 40 years, but we're not launching anything right now, so that won't help me personally. But what can we do? We can step up our efforts to try to find planets around the very nearest stars, just to leave something for future generations, and maybe those people are here now who can actually think about going there. And just like those founding fathers, I'm not talking today, so don't ask me, okay, about how we're going to do this. I just think it's a logical thing that someday someone will want to send a probe, even if it's intergenerational. And I didn't say we're going to put people on the probe, we're just going to want to send it. So how can we do this? So we want to find planets around the nearest sunlight stars. There are not that many of them. And at this point, I'm talking about beyond, right? I'm just giving you my own personal opinion, my own personal interest in what we might do. And I don't know if any of you noticed that with the things sitting over there. In the last few years at MIT, I've been working on an engineering project, and this is a little nanosatellite. How many people here have heard of CubeSats? Okay, great, I'm surprised. Is the CubeSat project going on here? No one else. Okay, there is talk, but what's happening is there is this phrase, 3 peas in a pod, and there's a phrase in engineering, 3 CubeSats in a pea pod. And a pea pod is a standardized deployer. At Cal Poly, they came up with this concept. They're having a conference actually the same week. But they actually have a standardized deployer that gets rolled into the upper stage of a rocket. And you have to have a standardized form factor in mass and volume. And you go on these upper stage of the rockets, and about 11 different launch vehicles launch these things, about 3 dozen of these have been launched. Mostly they're just single cubes, mostly student projects, and they go into orbit. And it's a project that you can actually work on as a student. Unlike a big space telescope, which you can never touch, you can work on it. And this particular thing actually, it's actually a demonstration model. This is not a flight engineering model. It doesn't have any real components that we really use. But what we're trying to do is make a little telescope that will point at one star looking for a transit. Just like we saw Kepler's looking at 150,000 stars to get statistics, we want to look at the very brightest, nearest stars to look for exoplanets that are transiting. And I'll be talking more about this in my next lecture, but suffice to say, we have proven the concept that as far as we need to, we are working on getting our final design, and we have a potential launch for our first prototype, which would be 2012 or 2015 through a NASA initiative. But you're welcome to come up and look at this later. And I'll talk more about this tomorrow. You can come and fool around with this. You even want to drop it. Real components. Here's a picture of what it would look like with solar panels. And there's a picture of 2 of my students who will be actually just very long here. So what we want to eventually is change a space science paradigm where we build and launch a prototype and eventually populate a constellation of different sizes. This looks a little too crowded. You can see how one constellation how it might look. I'm actually jumping around a little because I'm talking about beyond. I'm talking about a way to find planets like Earth around the very nearest stars. And exoplanets, we have another saying, all roads lead to terrestrial planet finder. And terrestrial planet finder is a collection of ideas where we do block out the light from that star. Remember, I told you it was 1 part in 10 billion. It's a way that you do block out light from the stars, and that also is a lecture tomorrow. And some of you might recognize this picture from a long time ago. But our goal, essentially, overall, is to find planets like Earth that have signs of life in the atmosphere. What we call signs of life, we call them biosignature gases. And it's really a complicated problem because biology is complicated, you know, and when people think about biosignature gases on other planets, they mostly just take Earth's biosignature gases. We call this a very terracentric view, but we're really at a loss of what else to do. This comes in lecture 3, actually. But I read this a few years ago in a National Academy of Sciences report, and I took this really seriously. We're actually thinking about finding life on Mars. Okay? Because how are you going to find life on Mars if you can't recognize it? Because the DNA is different, proteins are different. And this is a really serious issue here. Now, we're going to have to wait till lecture 3 to find out what we're trying to do about this. But overall, that's the goal, is to find planets that are nearby stars to leave a legacy for future explorers, and also to find the ones that we can get enough photons from to look at their atmospheres and to look for biosignature gases. So to summarize, discovery. Hundreds of exoplanets are known. There's over 1,000 more exoplanet candidates. Surprising discoveries continue, will continue indefinitely. And I'll just pause for a second and say people have asked me in the past, is exoplanets like a dot-com bubble? This is going to be an exciting field. It's always in the news and will just collapse. And the answer is absolutely not. It is because of that 10 to 15-year incubation period I mentioned. People are working in obscurity. One example is this exoplanets nanosatellite constellation concept. Working for a long time, trying to do new things, and as those technologies mature and come to fruition, more interesting planets will be found. In terms of characterization, I tried to tell you at least briefly that atmospheres and interiors are being studied in detail. The interpretation approach will change, actually. We'll still do individual objects, but we have this opportunity now to move to statistics. And beyond new efforts to find terrestrial planets orbiting the nearest sun like stars, it will emerge. It's an inevitable path forward. It is an inevitable path forward for us. And I will finish with a list of lectures. And thank you for coming out to my talk.